Okay, hello everybody. Thank you for coming to our fourth lecture. Today we're going to talk about how we deal with the data that we have before or during our actual machine learning. And we start with something that connects to what we did in the last lecture at the end. In the last time we were talking about the bias variance trade-off, we found out that the expected prediction error can be decomposed. We have a component that is influenced by the process itself that we have no control over, and that we cannot get rid of. We cannot get better than that. And we have one component that reflects the variance of the model that we estimate, and we have one component that reflects the bias, where the bias basically means the inability of the model that we chose to reflect, to approximate the actual underlying relationship in the data. And the variance is reflecting when we train the model with different draws of data, what different predictions we get for each run. So how can we estimate the bias and the variance? And there's a thing, an idea that is called bootstrapping. What is it? So the assumption that we make here is that the data that we already have is actually kind of reflective, or kind of reflects the actual underlying distribution. So we say that the data, the distribution that we observe, can be considered to be the actual distribution. And then what we can do is we can calculate the empirical cumulative distribution function. And we say, okay, the empirical cumulative distribution function is pretty much the actual cumulative distribution function. If both are identical, they are identically distributed. We are talking about the same distribution. And we can then draw basically a new data set from what we already have. So the idea is to generate new data sets from the data that we have. Then we can train the model on each of the newly generated data sets, and we can estimate the bias and we can estimate the variance. So let's write that down. Okay, so let's write down what do we mean when we talk about the empirical cumulative distribution function. So basically, we say the empirical CDF of X is just defined as the number of samples smaller or equal than X divided by the total number of samples. And how can we generate a new data set? Basically, this assumption that empirical CDF and actual CDF are identical means we can get a new data set simply by drawing with replacement from the data that we already have. So we generate a new sample by drawing uniformly. So we consider every sample that we already have equally, or if we have n samples, the probability to pick one of them specifically is 1 over n. And we just draw n new samples. So we get a whole new data set that is distributed in a similar fashion as the one that we already have. So let's visualize that a little bit. So first of all, what does it mean that the empirical CDF is equal to the actual CDF? So the empirical CDF will look something like that. And the actual CDF might be a little bit different. And look like this. But for our purpose, we can assume that both are pretty much the same. If we have enough data, of course. And then how would a bootstrap sample look like? So let's say the samples that we have are, for example, because we roll the dice 3 times. 1, 1, and 6. And the bootstrap sample now draws 3 times with replacement from this data set. So one bootstrap could look like this. It could be 1, 1, and 1, for example. So what would happen is randomly we get one of the 3. We could have gotten 1. We take randomly another one more time one of the 3. Could have gotten again 1, and so on. Basically, this allows us to train the model on each bootstrap sample as well. And then we can evaluate the performance, or we can evaluate the parameters for each of the bootstrap sample and get a better idea of the changes, if the random changes, that our model is subject to. due to the data that we have. So, of course, there are some assumptions here as well. For example, one assumption is that this statistic, that means, for example, the mean or the model or the thing that we want to estimate, it might not actually exist for the true distribution. However, it can exist for all finite samples or finite approximations. And in that case, the bootstrapping does not really reflect how the model would actually behave. And of course, do we have enough data? To justify that we assume that the empirical CDF is equal to the actual CDF. To give you a little bit better interpretation of what you can do with the bootstrapping. So you can also think about it not in terms of the cumulative distribution function, but you can think about it in terms of the probability density function, like a histogram, or basically similar to a histogram as well. So normally if you think about a distribution, you might be thinking about something like a bell curve, right? And when you draw a histogram for that, you will get a bell-shaped histogram. And you can think of the histogram that you get as being a valid approximation of the actual probability density function that you're dealing with. And then you can again sample from that histogram. When you do the sample, you basically, the last time when we looked at the bias variance trade-off, so how to use the bootstrapping. Last time we said the model and the prediction is actually a function of the data. And that means that when we have different data sets, let's say data set 1, data set 2, data set 3, we get different models and different predictions, maybe. corresponding to each of the data sets. And now we can calculate the statistic, for example, the bias or the variance in the prediction with those new samples. So you can, it's not a real algorithm, but you can think about it like this. First, you generate new data sets by drawing with replacement from the data set that you already have. Then you would calculate the model for each of the data sets, or so the parameters, the linear regression coefficients, or the predictions. For all of the data sets that you have, or that you have generated in step 1. And then you look at the variance or the mean or whatever it is, the confidence interval, whatever, the statistic of the xi that you are interested in. So you might be interested when you do linear regression, what you can expect, which accuracy you can expect from the prediction you have, from the prediction you made out of the data set that you get, that you have. And for that, what you can do is you can resample by bootstrapping, generate new data sets, calculate the linear regression coefficients or the linear regression model for each of the data sets, then evaluate each of the models at that specific point that you're interested in, and inspect the distribution that you get now. One, in my opinion, so you can also plot the histograms and so on. Like, you can just consider it like a new random variable that you can inquire about. One interesting thing to note is that the probability that a specific sample is part of the bootstrap actually is 63% when you have a lot of data. Now, why is that? Let's write that, note that. So the probability that a specific sample, di, is in some, or in the newly bootstrapped sample that you generate right now, it is, when you think about it, one minus So you draw n new samples, and the probability that you do not pick it every time is then 1 minus 1 over n to the power of n. And not picking it then for that you never picked it is then 1 minus this. And when you let n go to infinity, some of you might see that this approaches one minus e to the power of minus 1, so 1 minus 1 over e, which is approximately 63%. So that means that when you have a lot of data, when you have many, many samples and you bootstrap, one bootstrap sample will have only about 63% of your actual data in it. So it's like leaving out a third of the data and duplicating, or having a third of the data not represented at all, usually, and instead having some parts represented way more often. Okay, that much for the bootstrapping. So another question that you might be interested in is you want to know how well your model will perform on new data, right? You want to know how well it will generalize to the actual application. So normally when you get data, it's not that important to see the predictions of the model on the data set that you already got, because for that you already know it, but you want to know, but what it is important is how the model will perform on the data that it has not yet seen, the data that is not part of the training set, of the training data that you get. And for that, you can do something that is called the train and test split. So how does that work? What you're doing is you have your data set D with your data points D1, D2, and so on. And you split that into a training set. DI1, DI2. So you can choose that, for example, randomly. You can say you draw two-thirds, something like that, of the training data. You select for your of the data you have. You select for the training data, and the rest will become the testing set. You can extend this idea. So let's say, if you remember, we introduced the concept of regularization, and there was a regularization parameter, and there are theoretical results of how to choose that correctly. But normally you don't know. Normally the theory cannot help you too much, and you have to find out which one you should pick. And you can extend the idea of the train-test split, and you can split the data you have in a training and a validation and a test set. And for that, you basically say the data you got is split in training data, testing data, and validation data, where training, testing, and validation data set are mutually disjoint. And you can pick something like the validation set, maybe 10% of the data you have, and 20% for the testing data, and 70% for your actual training data. But it depends on the problem, so there's no general rule on that here. And what you do is train the model on the training part of your data set. You then evaluate the model, evaluate its performance for its ability to generalize on the testing data set. And you might go back to step 1 after you have changed the hyperparameters. And finally, you evaluate your model on the validation data set. So why do we have to make it so complicated? The thing is that even quite simple models might be able to approximate a data set extremely well. But their ability to generalize is extremely low, might be extremely low. So you cannot take the training data, the data that you fitted the model on, as the actual data for evaluating the performance. This is why we need the test set. Now, there's another problem. If we repeatedly go through this loop of saying we train on the training data, we evaluate on the test data, and we then tweak the model because we're not satisfied with its performance on the test data, then we might poison the well in some sense, and we might still overfit the model to the testing data because we have here the feedback loop from step 2 to step 1. So in order to actually know how the model would perform, we have to evaluate on its performance on something that was not used in the process of picking the model, of choosing the model at all, which is why we need the validation data set, why we need the validation part. And just saying picking 70% for training and 20% for testing and 10% for validation can be data inefficient. If you don't have a lot of data, this is not a good way to do it. And instead, you might be doing something that is called k-fold cross-validation, which is a version of that. And what we do here is we again take out our validation part, but now we're splitting our data set into k equally sized parts. So let's say k equals 5. We have 1, 2, 3, 4 parts here. And what we do, how do we call that? Part 1, part 2, part 3. Part 4 and part 5. And what we now do is first we train the model on the first 4 parts, P1 to P4, and test on P5. Then we retrain the model on P2, P3, P4, P5, and test on P1. Then we train on P1, P3, P4, P5, and test on P2, and so on. So we can actually train 5 models if you have chosen k equals to 5 and test 5 times, and we get a better estimate on how that works, how well the model performs. And again, we validate on the validation set in the end. So we can do this here several times. We can do, well, first we do this for each model, for each set of hyperparameters, we do it k times. For each of the parts we leave out. And we can then tweak the hyperparameters, change the model, and so on. Repeat the whole process. And finally, so for all choices of hyperparameters, finally we again evaluate on the validation data set. We can take that actually to its logical extreme, and we can train on the whole data set except for one single data point and calculate the error on that one data point that we left out, and do that for all data points we have, which is a lot of work. And that is called the leave one out error then. So if we have n data points, we perform n-fold cross-validation. We split the data sets into n parts minus the validation part. And we then calculate the average error that we get on the one sample that we left out each time. And that is what we call the leave one out error. Okay, that much for the training and testing split. So keep this in mind when you have to choose the model, when you have to tweak the model you should do the training and testing split. Also when you want to know how well your model will perform on unseen data. Basically all you have to do is to take out part of the data that you have, and you basically don't touch it at all during anything that has to do with choosing the model. And you only use it to calculate the final performance of the model. So the last time we also noted that we have a few assumptions that machine learning rely on quite fundamentally, quite strongly. And one of them was that we assume that the data is identically and independently distributed. And sometimes you might have to check if that is even the case. Or you want to know the likelihood that some idea, some hypothesis that you have, or not just the likelihood, but the probability of some hypothesis that you have, and you want to calculate that. So you might have something, a hypothesis like the coin that you're looking at is actually a fair coin. So the probability of heads equals the probability of tails. That is some hypothesis, right? And you can calculate something like a probability that this is actually true. given the data that you have. And for that, you can use statistic tests. So we might have questions like, is a coin fair? Is a coin flip a fair coin flip? Or can we reject the idea that the data is indeed identically distributed? And for that, there are several tests, and going into the huge variety of tests is a bottomless pit. So we're not going to dive too deep into it. You can normally you have to look up if you can find a specific, if somebody published a specific test for the question, for the hypothesis that you have at hand. For example, you can test if the data you have is actually normally distributed. So when you think back to the linear regression, in our derivation of the formula of how to get the coefficients for the linear regression, we assumed actually that the data, or at least the error of the data, is normally distributed. So you might want to know if it is a reasonable assumption that the errors that you get are actually normally distributed. And then you would need to look up the specific tests, the tests if a distribution is might be a normal distribution or not, and you can perform this test. What I want to show you here in the homework, you will derive a test for a fair coin to see how, in a very general way, how it works. And one test that I want to tell you about in the lecture is the Kolmogorov-Smirnov test, which can reject, which might tell you that you should reject the idea that the data you have, the training data, is identically distributed to the data that you have to predict in the model. And for a statistic test, normally you have something that you call the null hypothesis. That is basically the thing that you normally do not want, or the null hypothesis for the coin flip might be that the coin is actually fair. And you have reason to complain if you can reject the null hypothesis. So you have reason to believe that the coin is not fair if your statistic test tells you that you should reject the hypothesis that the coin flip is a fair coin flip. So how does it work? Normally, what you do is the null hypothesis must be something that is quite a strong assumption. Like saying the coins are fair is a very strong thing to say, because you say both probabilities are equal to 1/2. However, saying the coin is not fair is way more general, because it could be anything that is unequal from 1/2. So the way you do it is you derive from the null hypothesis probabilities of observing certain situations. So normally it works like that. You calculate how the probability of observing data that is at least as contradictory to your null hypothesis as a certain level. And if your data falls into this tiny part of the spectrum, so if your data actually is very different from what you would expect in the null hypothesis, and the probability to see something like that is extremely low, then you might think, okay, the thing is not that I observed something that is extremely unlikely, but the thing is that the coin is not fair. So you could say for the statistical test, for the coin flips, how let's say you flip the coin, somebody made you flip the coin, and he made a bet with you, and you lost every time. You did it 100 times, and you lost every single time. And now you might want to know, how likely is it that I lose every single time if the coin is fair? And you will find out that this has a probability of 1/2 to the power of 100, which is like close to 1/10 to the power of 10, which is like 10 billion, I think. Something like that. I hope I don't make a mistake here. You can calculate it at home. And which would be very unlikely, right? You would say, well, I don't believe that I'm the one who's so extremely unlucky. What actually happened is that the coin that you gave me is unfair. And you would reject the null hypothesis that the coins are fair. So for the Kolmogorov-Smirnov test, we say our null hypothesis is that the two distributions are actually identically distributed. And the way we do it is we again take the empirical cumulative distribution function. Or better, the two empirical cumulative distribution functions that we have. And then we calculate a distance of the two. So we have the two cumulative distribution functions f1 and f2, and we say the distance between the two is defined as the supremum over x of their absolute difference. The supremum is kind of a generalization of the maximum. Sometimes the maximum does not exist. For example, when you look at the function 1 over x and you just look at negative values, what is the highest value that the function achieves? Yeah, there is none. So it does not have a maximum. It comes arbitrarily close from below to 0, but it never reaches 0. And whichever number you pick, there's one that is a little bit bigger, as long as it's smaller than 0. So it has a supremum that would be 0. The supremum is the lowest upper bound that you can find, but it has no maximum. So and here we say the distance is the supremum of the absolute of the difference of the absolute, the supremum of the absolute value of the difference between the two, and we reject the null hypothesis. With level alpha if the distance between the two is greater than this statistic. And we say, and what does alpha mean? Alpha is the probability of rejecting the null hypothesis, even though it is true. So when you pick an extremely tiny alpha, the probability that you rejected the null hypothesis, even though it was true. So you say you claim the distributions will be different even though they are equal, and that you make this error will be smaller. The probability that you make this error will be alpha. So there's one thing to note: the test actually only works in one-dimensional data. It can be extended to 2 dimensions, but at least I don't know anyway how you could of a test statistic, of a statistical test that you could do to test the hypothesis or to test identity of distributions for higher dimensional data immediately. But this is something that it can be quite powerful already in and of itself if you're not in this setting where you have extremely high or very high dimensional data, like pictures, something like that. If you have a data set that is not that extraordinary, the Kolmogorov-Smirnov test might give you something very powerful to see if the data you get in the future, for example, is actually valid for the model. So what might happen is that you make some machine learning solution for a company, right? And you did this in, let's say, the last year, and now this year the company gets new data and your model performs very badly. And there might be several reasons for that, right? And one of the reasons might be that the data of this year is just completely differently distributed than the data you got last year. So the IID assumption, the assumption of identical distribution is violated, and you could kind of prove that with the test. Okay, so another thing that you might want to do when you get a data set is normalizing the data set. And that means you get the mean of the data and its standard deviation to 0. So why would you even want to do this? I'm sorry. So the standard deviation is not has this. Well, won't be equal to 0. It will be equal to 1. So why do we want to do that? What might happen is that you have basically different units in your data. So when you think about those two data points, we have 1 meter and 0.01 meter. And we have 1 meter and 1 centimeter. This is the same thing, right? But when you draw that in the meter axis, you get these 2 points, but in the meter centimeter axis, you get these 2 points. So one axis will be way more important if you have the centimeter axis will be way more pronounced. Now the problem, now it might not seem like a big thing here, but let's say you looked at 1 meter, 1 meter and 1 meter, then it's here 1 meter and 100 centimeters, and all of a sudden you have a completely different scale that you're talking about, and that influences the size of your the magnitude of your coefficients usually. So when you think about the linear regression, when you chose the meters as the axis, as the units for your problem, and you have, let's say, one coefficient is equal to 1, the other coefficient is equal to 2. When you have chosen meters and centimeters, all of a sudden, one of the coefficients would be 1, and the other coefficient would be 0.02. So two orders of magnitude smaller. And that's just because you use different units. If you had used kilometers instead, all of a sudden you would need a way bigger coefficient. And when you use something like a regularization, that will be extremely punished. So some methods actually need that your data is normalized in order to work properly, if you don't know anything else. So the best thing you could do is, if you know which things are the most important ones, or which features are the more important ones, then you would scale accordingly. However, if you don't know that, you normally default back to normalization. And libraries in Python, machine learning libraries, usually already have a function built in that allows you to perform this operation without you having to do it yourself. So to note down exactly what that means, let's calculate the difference between the two data points and the two units, two choices of units. So one time we have a difference of let's call that A, B. So in the meters, the difference of the two is 1/100th, but in the choice of the meters and centimeters, the difference is 1. So a machine learning algorithm that relies on the distance will be heavily influenced by something like that, by the scaling. And how do you how you transform the data? Basically, all you have to do is when you have a feature, a numerical feature, you map that to just 1 over the standard deviation of your feature times the feature minus the mean of the feature. Which is a very simple calculation. And just keep in mind that if your algorithms behave a little bit unusual or very different than you might expect, it might be due to a large difference in scale. And in that case, what you forgot is to do the normalization. The last thing that I want to mention is doing a visual inspection of the data. And you can do that in multiple ways. So you should look at things like a histogram, histograms, correlation matrices, which tells you how two features are correlated. So if there's some kind of linear dependency between the two features, you can look at, which is also something important because it might change. You can check the headers and the names and the units of the features. You can make, maybe, if it's two-dimensional, make a plot of the data. And if it's high dimensional, you might use a dimension reduction technique, something like random projections. Or TSNE. And then you might be able to identify clusters. Or outliers. So outliers can be something like an error in the data. When a human typed in, a human acquired the data, or there's a measurement error, they might have a fat finger, and they might write 100 million instead of, because they hit too many times the 0 instead of 1,000. Or let's say 1,000,000 instead of 1,000. And all of a sudden you have one value that is extremely out of range, and you can identify it like that, because it might, some techniques are very sensitive to outliers of that form, and that might actually influence the result that you get. Yeah, and there's one more thing that I want to mention, and that is that one always has to be careful with random events. So when you have, for example, a company with, let's say, 10,000 stores, and you have to analyze customer behavior for the company, then you might find something like that there's one store, when you inspect the data for some reason, you might find one store where the relationship is extremely simple. Everybody only buys cat food. Now, is that something meaningful? Is it an actual rule in some sense that people only buy cat food? Most likely not. The thing is that you have so many stores that just by chance one store is right next to maybe animal shelter, and so they are the main customer and they buy the cat food. But it has nothing to do with the company as a whole, but it's just a random effect, because you have so many, can look at so many combinations that some of them might look especially easy, but it's just a random effect that you're observing. And focusing on that would be cherry picking. Basically, you pick only the things that you like and forget or leave out all the things that don't fit the narrative. And that is a very dangerous thing. So it might happen in a very benign setting. So the company that you work for, or the people who give you the data, they might tell you, yeah, actually, there's this 1 month where everything is way easier than usual. We don't really know why, but so that that your machine learning works better, we thought we give you this month's data. That sounds like a good thing, right? But you really have to be aware of why. You should really know why this month was an especially good month. Because if it was a good month just out of randomness, out of random effects, then your results that you get might be seriously jeopardized. So only do a selection of the data or focus on something that looks more easy if you actually know what you're doing, and don't do it just because you had this huge variety and you were able to, you found one that for some reason that you don't know just looks a little bit better. So that much for dealing with the data that you have. And we're going to talk in the next lecture about the first real algorithms. So now basically we did the foundation of first how things work on a very abstract level, in the first 3 lectures, we were talking about things like mathematics, the linear algebra, understanding how the models work and how we can calculate, how we can manipulate them. In the second lecture, we were looking at how optimization processes work, how the training of the model actually works. In the third lecture, we found out how all of that actually connects to probability theory, to how we conceive the setup that we are in an abstract level, in a theoretical way. So this is what we're actually doing. Actually, what we're trying to do is estimating distributions, right? And now we know what we have to do with the data when we work with a machine learning procedure. And from the next lecture on, we can do the actual machine learning methods. So thank you very much. Thank you for your patience. And let's see you next week. Bye-bye.